Hey everyone, so in this video we're going to be talking about probability, which is one of my favorite subjects to talk about. So let's go over some terminology. An experiment is any activity in which there are at least two possible outcomes and the result of the activity cannot be predicted with absolute certainty. So an easy example of this would be if you flip a coin once. The act of flipping the coin one time is the experiment. And then we have what's known as the sample space, and we're going to denote this by a capital S. And the sample space is the set of all possible outcomes of an experiment. So for the coin flipping example, the set of heads and tails would be the sample space. And an event is a set of one or more outcomes from the sample space, and the event happens to be a subset of the sample space. And we usually use capital letters other than S, such as A and B, to denote these events. So let's look at an example. So let's say we flip a coin twice and we record the observed outcome. And to make things easy, we're going to use H for heads and T for tails. And so what would the sample space be in this case? Remember, the sample space is the set of all possible outcomes from an experiment. So what could possibly happen if we're flipping a coin twice? Well, we could get heads and then heads. We could get heads and then tails. We could get tails and then heads. And then we could get tails and then tails. These are the only four outcomes that we could possibly end up with. So in this case, this set right here is what makes up our sample space, S. And then the events don't necessarily have to just be one particular outcome of an experiment. It could be any subset of the sample space S. So we could say something like, well, let's define A to be the event in which we flip exactly one tail. So in this case, A is going to be any of these events that have exactly one tail. So in this case, it looks like these two are the only two that have exactly one tail in them. So the event A is going to be made up of HT and TH. All right, so let's go over some notation that's worth knowing before we learn a little bit more about probability. So for any two events A and B, this right here means the intersection of A and B. And this represents the outcomes that are in A and B. So any outcomes that are both in A and in B, that's what we're going to call the intersection of A and B. And the way I actually remember this is we're using the keyword and here, and this upside down U symbol that we use to denote the intersection kind of looks like the letter A, except without that crossbar in the middle. So that's an easy way to remember that. So we read this as A intersect B. Now we also have what's called the union of A and B, and we use this to denote the union of A and B. An easy way to remember this is that the union looks like the letter U. So that's really nice. So this represents any of the outcomes that are in A or B. And we'll go over some examples of the intersection and the union shortly here. So now this symbol right here, this 0 with a slash through it, is known as the empty set. And this is a set that contains no elements. And then finally, we have what's called the complement. So for an event A, the complement of A, we're going to denote by A with this little tick symbol up here. Sometimes instead of a tick symbol, it's the letter C. Or sometimes people will draw a horizontal bar above the letter A and use that to denote the complement. So just be careful of that. Depending on where you look, sometimes people use different symbols to denote the complement of A. But for right now, we're going to be using this symbol to denote the complement of A. And the complement of A is the set of outcomes that are not A. So you could think of it as the opposite of A. And we'll go over some examples that involve the complement as well. So let's look at an example. So let's say we roll a fair six-sided die. And in this case, the sample space which, remember, the sample space is the set of all possible outcomes from the experiment. In this case, our sample space is going to be 1, 2, 3, 4, 5, and 6, because those are the possible outcomes from rolling a fair six-sided die. And we can define some events here. So we can define A to be the even numbers, 2, 4, and 6. We can define B to be the odd numbers, which are 1, 3, and 5. And we can define C to be any of the numbers that are 4 or higher. So that's going to be 4, 5, and 6. And remember, these are just events, so they're subsets of this sample space S. So now we can do things like this. We could say, like, all right, what's A union B? In A union B, remember, it's any of the outcomes that are in the event A or in the event B. So let's just take it one by one here. So is the number 1 in A or in B? And the answer is yes, it's in B, so that means it's in A or B. Same with the number 2. We could say, is the number 2 in the event A or in the event B? Well, it's not in B, but it's in A, so we can include that in A union B. So if we did this for all of them, and it looks like all 6 of these numbers are going to be in A union B. So A union B is going to be our entire sample space. So we could do this with the intersection too. We could say, all right, what's A intersect B? So now we have to be careful. A intersect B is the set of any of the outcomes that are in A and B. So is the number 1 in A and B? Well, it's in B, but it's not in A. So in this case, we can't include 1 in the intersection. Same with the number 2. It's in A, but it's not in B. So we can't really include that in the intersection either, because it has to be in A and B for us to be able to include it. So if you do this with all 6 of these numbers, you're going to find that none of these numbers are going to be in A and B. And why is that? Well, that's because A is the even numbers and B is the odd numbers. So in order for something to be included in A and B, A intersect B, a number would have to be even and odd at the same time. So it kind of makes sense that we end up with the empty set here. And we could also look at A intersect C. And remember, A intersect C is the set of outcomes that are in A and in C. So let's go one by one. It doesn't look like 1 is in either of these events, so we can't include that. 2 is in A, but it's not in C, so that means we can't include it in the intersection. 3 doesn't look like it's in either of those events. The number 4, however, it's in A and it's in C, so we can include that in our intersection. For the number 5 is in C, but it's not in A, so that means it's not in C and A. And then finally, for the number 6 is included in A and in C, so we can include that in our intersection. So altogether, we end up with an intersection of 4 and 6 for A intersects C. Then we could also look at A union C, and this is the set of outcomes that are in A or in C. So this is pretty easy. I mean, if you want, you could actually just list these out. You could say, all right, 2, 4, 6, and then we already counted 4, and then we can include 5 in there because that wasn't in A, and then we already counted 6. So if you want, you could just kind of list these out and then eliminate the duplicates. So this is going to be 2, 4, 5, and 6. Then we have down here, we have this B intersect A union C. And this looks a little bit complicated, but it's really not so bad once you take it piece by piece. And this part right here is what we want to do first because it's in parentheses, just like order of operations. But the nice thing is that we already computed what A union C is. We found that A union C was this 2, 4, 5, and 6. So if we want to find what B intersect A union C is, we need to find what the intersection of B and 2, 4, 5, 6 is. And that's not too bad because we know B is the odd numbers. So basically all we need to do is look at this and find what numbers are in this set, but also odd. And that would be B intersect A union C. And it looks like the only odd number in this set is the number 5. So altogether, B intersect A union C is going to be the number 5. So once again, I did this piece first because it's kind of like order of operations, and then you look at what intersects with B from that set. And then down here, we're going to be looking at the complements. So what's C complement? Well, remember the complement we defined to be the opposite of C. It's whatever is in the sample space S that is not in C. So in this case, since C is 4, 5, and 6, we want to find the numbers that are not 4, 5, and 6. So if we want, we can come up here and we can highlight the 4, 5, and 6. This highlighted part is going to be C. So what's left? We're left with 1, 2, and 3. So the complement of C is going to be 1, 2, and 3. The other way you can think about this is remember that C was any number 4 or higher. So the opposite of numbers 4 or higher are numbers below 4. And the numbers on a die that are below 4 are 1, 2, and 3. So that's another easy way to get C complement. And then the last thing we're going to look at is B intersects C, all of that complement. So the first thing we have to do is we have to find what B intersects C is, because that's what's in parentheses, and then we have to take the complement of that. So what's in B intersects C? So B intersects C, remember, it's the set of outcomes that are in B and in C. So basically all we need to do is look at what this set and this set have in common. And it looks like the only thing that's in both sets is the number 5 here. So B intersects C is going to be the number 5. So this whole thing is the number 5. And what we want is the complement of the number 5. So all we need to do is look at the sample space and we just take what's not the number 5. And that's everything else. So that's going to be 1, 2, 3, 4, and 6. So our B intersects C, all of that complement is going to be 1, 2, 3, 4, and 6. Okay, so now it's probably a good time to define probability. And probability is simply just how likely an event is to occur. You could also think of probability as the long run relative frequency of an event. And what do I mean by long run relative frequency? Well, for example, what's the probability of getting heads when you flip a coin? It's 0.5. There's a 50% chance of getting heads when you flip the coin. But if we look at this in terms of relative frequencies, remember the relative frequency is the frequency divided by the total number of observations. So if we flip the coin 10 times and we end up with 7 heads, that's totally within the realm of possibility of happening. But our relative frequency there would be 0.7. So what we mean by this long run relative frequency is that theoretically, in the long run, if we flip this coin infinitely many times, or a very, very large number of times, then eventually our long run relative frequency will be roughly 50%. And that's what we mean by probability. So that's just an alternative way to think about it. If you want to think about it simply as how likely something is to occur, that's totally fine too. All probabilities are between 0 and 1. So in the coin flipping example, the probability of heads is 0.5 and the probability of tails is 0.5. A probability close to 0 means an event is not likely to happen, and a probability close to 1 means an event is very likely to happen. For an event A from S, we use this capital P and then the A in parentheses, P of A, to represent the probability of A. So if the probability of heads was 0.5, we would say capital P with H in the parentheses here, and then that would be equal to 0.5, probability of A. So if probability of A is equal to 1, that means A is guaranteed to occur. If the probability of A is equal to 0, that means A will never occur. And there are theoretical situations where this might not be technically true, but we're not going to cover those for all intents and purposes, you can think of probability of A equal to 0 implying that there's no possible way that A can happen. But for any two events, A and B, from the sample space S, A and B are said to be disjoint or mutually exclusive if they can't happen at the same time. So again, I know I keep bringing up this heads and tails example, but that's a perfect example for this. You can think of heads and tails as being disjoint or mutually exclusive events because they can't happen at the same time. And if we were to express this in set notation, we would say heads intersect tails is equal to the empty set. And that's how you can say that something is disjoint or not. If the intersection is the empty set, then they can't happen at the same time. And here's an illustration of that. We have the event A and the event B. If you want to think of this as heads and tails, you can do that. But basically, what we're saying here is that these two events from our sample space S don't have an intersection, which means they can't happen at the same time. And that's how we know they're disjoint. So let's look at a couple examples here. Well, I actually already went over this example. You flip a fair coin, heads and tails are disjoint. So let's look at the next example. So let's say we draw a card from a standard deck of playing cards. We can say K is equal to drawing a king, and Q is equal to drawing a queen. Well, you can't draw a king and a queen at the same time, so those events are disjoint. But if you said, for example, let's let K equal to king and the letter D equal to diamonds, then is it possible to draw a king and a diamond at the same time? And the answer is yes. You could draw the king of diamonds. So in that case, king and diamonds aren't disjoint events. But the example here, king and queen are disjoint events. So they're disjoint again because they can't happen at the same time. And then we have a rule down here that we're going to touch a little bit more on in a little bit. But if A and B are disjoint, then the probability of A union B is equal to the probability of A plus the probability of B. And this is known as the addition rule for disjoint events. So now let's talk about what's called conditional probability. So for any two events, A and B from S, this right here means the probability of A given that B has already occurred. So this vertical bar right here stands for given. So we read this as the probability of A given B. So B has already happened, so now what's the new probability of A now that B has already happened? And a very important theorem that relates to conditional probability is called Bayes' theorem. And Bayes' theorem says that the probability of A given B is equal to the probability of A intersect B over the probability of B. And we're going to be talking about this a lot in a couple of examples coming up, but this is what Bayes' theorem says, and Bayes' theorem is very important. And then down here, we have a multiplication rule, and realize that this is just a rearranged version of what's above here. But the reason why I'm including this is because it's a little bit more intuitive to see. So if you look at what's going on here, this is the probability of A intersect B, which is the same thing as saying the probability of A and B. And then what we have over here, this is the probability of B happening. And then given that B happened, what's the probability of A also happening? So this is just like saying B happened and then A happened. Or in other words, A and B happened. So this is a little bit more intuitive to see than what's going on up here, but this formula up here is what's more commonly used. Okay, so now let's talk about independence. So for any two events, A and B from S, A and B are said to be independent if the occurrence of A does not affect the probability of the occurrence of B, and vice versa. So in other words, A and B are independent if and only if the probability of A is equal to the probability of A given B. So think about what this is saying. So if B happened already, which is what this given B part is telling us, and if A isn't affected at all by whether or not B happened, then this probability of A is going to be the same as this probability of A. So if it's unaffected by B, then this given B part is kind of meaningless to us. So we can express it this way. So as you might expect, if A and B are not independent, then they're said to be dependent. And then down here we have an alternative definition for independence, which is that the probability of A intersect B, or the probability of A and B, is equal to the probability of A times the probability of B. And this is known as the multiplication rule for independent events. So let's look at an example to get a feel for what it means for two events to be independent. So let's flip a fair coin twice. And we could let A be the event that we get tails on the first flip, and we could let B be the event that we get tails on the second flip. Now, think about what happens when we're flipping a coin twice. Is the outcome of the second flip affected at all by the outcome of the first flip? No, you still have a probability of 0.5 of getting tails on the second flip, regardless of what happens on the first flip. So that means A and B, the event that we get tails on the first flip and the event that we get tails on the second flip, are going to be independent events. So let's look at some properties of probability. So for any two events A and B from S, the complement rule says that the probability of A complement is equal to 1 minus the probability of A. The addition rule says that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. And this looks kind of messy, but it might be helpful if we look at a picture to see exactly what's going on in this formula. So what we're looking for is the probability of A union B. So this whole rectangle is the sample space S, and A union B is going to be this peanut-shaped object right here. Because the red circle is A, the green circle is B, and we want their union, meaning we want everything that's in A or in B, which includes their intersection, which is right here. So how do we calculate the area of this peanut-shaped object? Well, it seems natural that we might want to add the area of this red circle and the area of this green circle. And that's what we're doing when we say the probability of A plus the probability of B. It's this red circle plus this green circle. But the problem is we're trying to get the area of this object, but we counted this middle part twice because when we added the area of this red circle, we counted that middle part, and then we added the area of this green circle, and this overlaps. So we have to subtract off one of these intersections for us to get the area of this entire object. And that's why we subtract off the probability of A intersect B. And altogether, what we end up with is the area of this object, which is the probability of A union B. And then we have the addition rule for disjoint events, which we covered earlier, but let's go back to it. So remember with disjoint events, we had the red circle here and the green circle here. And since they're disjoint, they don't overlap with each other. So the total area, which is their probability, the total area of them is going to be the probability of A plus the probability of B. We don't have to worry about any overlapping. So that's what's nice about disjoint events. And then we talked about Bayes' theorem already, which says that the probability of A given B is equal to the probability of A intersect B over the probability of B. And then we talked about the multiplication rule already, which is the probability of A intersect B is equal to the probability of A given B times the probability of B. And the multiplication rule for independent events, which we talked about already, which is the probability of A intersect B being equal to the probability of A times the probability of B. So let's look at an example. So we're going to roll a fair six-sided die, And we want to know what's the probability of rolling an even number. So on a six-sided die, there are three even numbers, 2, 4, and 6. So what we want is the probability of rolling a 2 or a 4 or a 6. And the key word here is or. What that tells us is we're looking for the union. We're looking for the probability of 2 union 4 union 6. So we can't roll any of these three numbers at the same time, which is kind of nice for us because that tells us that they're disjoint. And now we can use the addition rule for disjoint events to say that the probability of 2 union 4 union 6 is the same thing as the probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6. And we know that the probability of each of these is 1/6. So this is going to be 1/6 plus 1/6 plus 1/6, which means the probability of rolling an even number is a half, which we kind of felt like that was going to be the case anyway, but this is how we mathematically show that this is the probability of rolling an even number. So let's look at another example. So let's say we flip a coin 3 times. What's the probability of getting tails on all 3 flips? So we're interested in the probability of getting tails on all 3 flips. And another way of saying that is we want to get tails on the first flip and tails on the second flip and tails on the third flip. So in other words, what we want, using the keyword and, this tells us we're looking for intersections here. We're looking for the probability of tails on the first flip and tails on the second flip and tails on the third flip. And just like we said earlier, these coin flips are independent. The outcome of the second flip isn't affected at all by the outcome of the first flip. And same goes with the third flip. So all three of these coin flips are independent of each other. And now that means we're allowed to use the multiplication rule for independent events. And that tells us that the probability of tails intersect tails is the same thing as the probability of tails times the probability of tails times the probability of tails. And that's equal to 1/2 times 1/2 times 1/2. And that's going to be 1/8. All right, so let's look at another example here. So suppose 44% of households own a dog, 29% of households own a cat, and 17% of households own a dog and a cat. So what's the probability that a household owns a dog or a cat, and what's the probability that a household owns a dog given that they have a cat? So first of all, before we try to answer these questions, let's try to simplify things a little bit. So let's use the letter D for dog and use the letter C for cat. And before we want to do anything else, it's probably helpful to take the information that we've been given here and kind of put it into symbols, because that'll help us use the formulas a lot more effectively. So we're being given this 44, this 29, and this 17. So how do we express those in terms of probabilities? Well, 44% of households own a dog, so that means the probability that a household owns a dog is 0.44. And we're told also that 29% of households own a cat. So the probability of cat is 0.29. And then we're also being told that 17% of households own a dog and a cat. And that keyword and here tells us that this is going to be an intersection. So the probability of dog and cat is equal to 0.17. And if we want to draw a picture of this, this kind of looks like our Venn diagram from earlier of the events A and B, but now it's just the events D and C. So what's the probability that a household owns a dog or a cat? And again, we want or here, so that tells us we want the union. So we're trying to find the probability of dog union cat. And here we can use the addition rule, and it gives it to us explicitly. The probability of dog union cat is the probability of dog plus the probability of cat minus the probability of dog intersect cat. Now remember, this was the formula that we had from before when we double counted the middle and we had to subtract that piece in the middle off. So when we use this formula, we're able to get 0.44 plus 0.29 minus 0.17. So the probability that a household owns a dog or a cat is 0.56. And then the second part of this question is, what's the probability that a household owns a dog given that they own a cat? So this word given here tells us that we're dealing with conditional probabilities. So we're looking for dog given cat. And remember, when we were dealing with conditional probabilities, we're almost always going to be using Bayes' theorem for this. And Bayes' theorem tells us that the probability of a dog given cat is equal to the probability of dog intersect cat over the probability of cat. And that's equal to 0.17 over 0.29, and that's right around 0.59. So we have one more example here, and this one's actually a little bit tricky. So suppose a basketball player's free throw percentage is 80%, and we want to know the probability that the player makes at least one free throw in the next 5 attempts. Now, one way we could do this is we could list out each of the possibilities of what could happen, like make, miss, or make, miss, make. And we could list all of those out and count how many of those possibilities include at least one free throw, and then calculate each of those probabilities and then add them up. But that's really tedious, especially because there are 32 different possibilities of what could happen. So we're going to have to think of a simpler way to do this. So again, just like before, we want to put this into symbols. So the player's free throw percentage is 80%. So that means the probability of a made basket is 0.8. And since the complement of making a basket is missing a basket, the probability of missing a basket is 1 minus 0.8, which is 0.2. We're using the complement rule to say that. And the way to make this problem a lot simpler is to observe that the complement of at least one make is to miss all the baskets. Because think about it. If the player makes the first basket, the player's already made at least one basket. Or if the player makes the fourth basket or the second basket or two of the baskets, the only way that the player could not make at least one is to miss all of them. And this makes the problem a lot simpler because we could use the complement rule to say that the probability of at least one make is equal to 1 minus the probability of missing all of the baskets. And this right here is a lot easier to work with than this right here. So what does it mean to miss all the baskets? That means that the player missed the first basket and missed the second basket and missed the third basket all the way up to the fifth basket. And we can use the intersection symbol to say that. And the other thing we can make note of here is that each of these shot attempts are independent of each other. The probability of making or missing the second shot is not at all affected by whatever happened on the first shot attempt. So since these are independent and we have an intersection here, we're allowed to multiply each of these individual probabilities. So we could turn this whole thing into the probability of missing the first shot attempt times the probability of missing the second shot attempt, all the way until we multiply by the probability of missing the fifth shot attempt. And we found earlier that the probability of missing a shot attempt is 0.2. And so we're multiplying 0.2 by itself 5 times, and that's what we have down here. And when we multiply something by itself a certain amount of times, that turns into an exponent. So this is 0.2 raised to the fifth power. So order of operations, we do the parentheses and exponent. So what we're left with is 1 minus 0.00032. And that comes out to 0.99968, which sounds pretty high, but think about it. If the player makes 80% of his shots, you'd have to think that the player would have a pretty good chance of making at least one of their shots. So this makes a little bit of sense. This is really close to 1, so it's very, very likely that the player will make at least one shot of the 5 attempts. So anyway, that's all for this video. I hope you found it useful and enjoyable with probability 1, and I will see you in the next video. Take care.